Well, good morning, ladies and gentlemen, and welcome to our final installment of Chapter 1 for Calculus. This is our last glue-in for this chapter, and after this we'll be looking at a review and then a test based on the stuff we've covered so far. And today you'll see we're smushing together 3 sections, and we have section 1-4, which we've kind of started before. It's the parametric equations. We're going to look at that again. And then after that, we're going to talk about the unit circle and what you need to know in order to be successful on the AP test. So with our parametric equations this time, we're going to go the other way around. Instead of being given the parametric equations, we want to find parametric equations for certain situations. So in this case, we want to find a parametrization for a line segment with these endpoints. And I'm going to do this in 2 ways, and I guess it depends on your preference for which you like better. But I just want to present it 2 ways so you can see how multiple answers could result from this. So let's see, we're finding a pair of parametric equations with these endpoints, and I'm going to call this first method, we'll call this domain restriction. So I'm going to call this first method domain restriction, and we'll notice that we have points, and we're trying to find the line between those points, essentially. So what I'm going to do is I'm going to find the equation through those points. So I'm going to do the whole process. I need to find the slope first. So subtracting the y's, subtracting the x's. So we do 5 minus 1, 4, so we got 4/5. 4/5 is the slope. So then again, we need to find the equation of this line. So we'll do the y equals mx plus b form. So y equals 4/5 x plus b. And then I'm going to plug in, that point looks easier. 5 equals 4/5. X is 3 plus b. And now we're solving for the y-intercept. Let's see, we have a fifths here, so that means we need this to be fifths. So this is 25/5 and 12/5 plus b. So that means, let's see, that means b is 13/5. So we can put that all together. The equation of the line between those points is 4/5 x plus 13/5. So that's the equation of the line, but that is in Cartesian form. So I'm calling this domain restriction. In my mind, this is kind of the easiest way to do it, but I mean, I'm a math teacher, so sometimes I lose sight of the forest for the trees. So here's, this is domain restriction. So we know that parametric equations have t's instead of x's for the independent variable. So I'm going to make this substitution right here. I'm going to say x equals t, and then y equals 4/5 t plus 13/5. So this is my parametric equation pair right here. 4/5 t plus 13 over 5 is the y, and then x equals t. So you can imagine we could go backwards, x equals t, plug that into t, and then now we have our Cartesian form. So I think it's this little step right here that makes this the easy way, because x equals t, so we'll just go back and forth, plug in x for t here, and now we have the Cartesian. But what we have to do here is restrict the domain, because if we graph this piece right here, that would just be a line going from -infinity to infinity. But we want the x values, aka the t values, to go from -2 to 3. So I'm going to restrict my t interval to those x values. And then, broken pencil. That'll give us our parametric equation. Grab another pencil. Get that out of here. So I call that domain restriction, and if you graph that, you'll see we get the line segment between those points. So another way to do this is by creating an easy t-interval and then finding equations to spit out these points right here. So I would call this, I don't know, the easy t-interval. And we'll do it by design. Easy t-interval by design. So we're trying to create equations, two equations that spit out the x coordinates and that spit out the y coordinates. So maybe to make this easier to see, the t is the independent variable and we're trying to get an x coordinate. So if I look back at my points, maybe I should zoom out here. Wrong way. So I'm trying to start with an x value of -2. I'm trying to start with an x value of -2 and get an x value of 3. And here's where my easy t-interval by design occurs. I'm going to start with a t value of 0 and then end at a t value of 1. And then I'm going to do the same thing for my y coordinates. Again, the t is the independent variable, and my first y coordinate is 1, and my second y coordinate is 5. And then I'm going to use an easy t-interval going from 0 to 1. So we'll notice that our x values start at -2 and go up by 5. And then our y coordinates start at 1 and go up by 4. All right, so I'm going to zoom down here and zoom in. So I can easily make an equation that does this. So I go up by 5 and I start at -2. And then my y values go up by 4, but start at 1. And then my t-interval, by design, is going from 0 to 1. And if we plug that into our calculator, we'll see we get those endpoints right there. So, two ways to do this: domain restriction and easy t-interval by design. Then the other thing we're going to talk about in this section, and I'm going to zoom out here, is the unit circle. And I guess I should really point out that this entire glue-in has been done without a calculator and will continue to be done without a calculator. On the AP test, portions of that test, you're not allowed to use a calculator, so we need to get used to no calculator problems. And in particular, you're going to be required to find the sine and cosine of certain angles on the unit circle. And you're going to have to come up with a convenient way to memorize these values. So that's what we're going to do right now. We're going to draw the upper half of the unit circle. So we're going to draw the upper half of the unit circle. Ooh, look at that circle. Looking good. So I think the important thing to remember about the unit circle is that it's cut into 12ths. That's hard to say. It's cut into 12ths. So here at the beginning, this is 0 pi over 12. And then way over here is 12 pi over 12, which is just 1 pi. So then up here, it's cut into 12ths, remember. That is 6 pi over 12ths, which is half a pi. What's up? And it's obviously a beautiful day for math because Hong is here, and I'm making the video for the next section, so just make sure that's ready to go. So again, we're talking unit circle, and it's important to remember it's cut into twelfths. So I'm going to cut this up into twelfths, but I'm going to skip the first one, and then go 3, skip the next one, and then go by 3s. So we started at 0, but we skip 1. So the next one is 2 pi over 12, and then 3 pi over 12, and then 4 pi over 12. We skip 1, the 5th, and that gets us 6 pi over 12, and then skip 1 again. So the next one is 8 pi over 12, 9 pi over 12, and 10 pi over 12. And these can all be simplified, and I'll have you do that on your own, but you can simplify these radian measures right here. And the other piece of this is that the x and the y coordinates are the sine and cosine values of that angle measure. So all along this unit circle are the x and the y coordinates, and those represent the cosine of the angle and the sine of the angle. So if we start going in order, cosine of 0 starts with 1. What's up, Kenny? It's obviously a beautiful day for math. Kenny's here now also. And so the cosine value is 1. So that x value is 1 way over here. The radius, the circle of radius 1. And then it starts going down. Root 3 over 2. Root 2 over 2. And then root 1, which is just 1 over 2, 1/2. And then down to 0. And then now we go in the backwards direction. These are negative x values. So negative 1/2. So notice the pattern here. So 1/2, the next one is going to be root 2 over 2, but negative. And then root 3 over 2, negative. And then remember the pattern, that was a positive 1, now it's negative 1. So those are the x values. And then the y values, so right here, the y value starts with 0. And then remember the pattern, from 0 it went to 1/2. And then from 1/2 it goes to root 2. And then after root 2 is root 3. And then root 3 to 1. And then the pattern repeats itself. Root 3 over 2. And then back down. Root 2 over 2. 1/2. And then 0. So now you've constructed this by memory, you could easily find the sine of pi over 2 or the cosine of 3 pi over 4 once you've simplified these all down. So you're now ready to work on these problems right here, and after this, review and then test. Enjoy.